Welcome everyone. In today's video, I'll be discussing about an important concept in machine learning based modeling called regularization. Let us try to understand what regularization is all about, why is it used, and how it can be implemented in the context of regression modeling. So to start with, let us understand what is regression all about and also try to understand what is model complexity. In regression, what we are trying to do is to find an approximate solution for an overdetermined problem. So let us say we have an overdetermined problem, a beta approximately equal to y. Y is the output feature vector, a is the data or feature matrix, beta is the coefficient vector. So what ordinary least square based regression tries to achieve here is to find the optimal beta that can best explain y based on the parameters or the features in A. So the objective function of ordinary least square can be written as argmin of beta, L beta, well L beta is a loss function where L beta is given as norm of y minus a beta. So the idea here is to find the optimal beta for which y minus a beta, y is the predicted variable and a is the input matrix, input vector or feature matrix, and beta is the coefficient. So where y minus a beta is the minimal. So where we are trying to say is, what we are trying to say here is that the loss should be minimum. Please understand that we are dealing with an overdetermined system of equation, so it will y minus a beta will never reach 0 in most cases, and that we are only trying to minimize this y minus ab, which is L beta. And once you obtain this optimal beta, you can plug it back to this equation, and now this equation can predict y for any future inputs. And now let us discuss about model complexity. The complexity of a model represents the complexity of function that it is trying to learn. So in this case, we have a set of input feature vectors that is available in A, and we are using some particular combination of these input feature vectors or their higher order combinations to predict y or estimate y. So as the model uses more and more features in A to predict y, we say that model is complex. So if the model is using a less number of features to predict y, then we say the model is simpler. Now let us try to understand the relationship between modeling complexity and modeling error. So when we try to evaluate the model complexity, we have two types of errors that we look at. One is the training error and one is the testing error. So as the model becomes complex, you can see that the training error gets lower and lower. This is because the model is getting better and better in capturing the trend in the training data. But when a new data set, like a testing data set, which the model has never seen, comes into picture, modeling error first decreases, and then after a particular modeling error or testing error increases. Now you can see that there are two zones in this particular graph. One is the underfitting zone, where you can see that both training and testing error are decreasing. This will decrease up to a particular point, and you can see that interestingly after that, even though the training error decreases, the testing error increases. So this right zone is called overfitting zone. So we are looking for a model which works in this particular modeling complexity where we have minimal testing and training errors. Now let us look at a real example and let us try to understand it even better. So on the right hand side, you can see that there is a relationship that we are trying to build between age and the risk of getting heart disease. The simplest model that you can try to fit is a linear model, of course. But the problem here is that it results in underfitting. It is not completely exploring the trend in the data. So you can see that this model falls in this particular section in the model complexity graph. Now let us try to improve the model or make the model a little more complex so that it can capture more trend in the data. So here we have used a polynomial model, and you can see that the model is able to more closely follow the trend in the data, and it is almost reaching close to the optimal model complexity line. But we can do even better, right? So it has not reached the optimal line. We can even push it further. Let us try to implement a higher order polynomial and try to see if the model complexity is increasing. So now we are trying to fit a higher order polynomial onto this particular data set, and you can see that the model captured all the trend in the training data. But when it comes to testing data, the model completely fails here. And this is a situation where the model overlearns. But this is something that we should avoid it. So this is where regularization comes into picture. So what we are doing with regularization is to take a complex model and try to reduce the complexity of the model to bring it in the optimal zone. Before going to the mathematical concepts of regularization, let us try to understand two things. One is the 3D visualization of how a loss function will look like. So this is how a loss function with two parameters, beta 0 and beta 1, look like for ordinary least squares. What you see on the xy plane here is iso circles or iso lines, which are basically locations where loss function is a constant. And you can see that as you move further and further away from the optimal beta 0 beta 1 combination, the loss increases. Going forward, let us try to understand how norm function look like. So for a particular vector beta with elements beta 0, beta 1 all the way up to beta n, the nth norm can be written as I equal to 1 to n mod of beta the whole raised to L raised to 1 by L. And you can see that each of the norms L1, L2 and L infinity have a different set of geometrical properties. So you can see that L1 norm have a rhombus shaped isolines. For the L2 norms, the isolines are in the form of circles, and for L infinity norm, it's more like a square. Okay, now we have understood the geometrical properties of loss function and norm function. Now let us understand how regularization is performed in the context of regression. Now let us consider this particular example. Here we are trying to evaluate the risk associated with a person to have a heart disease or not based on several other factors. Which are the factors? So the factors include age, sex, BP, sugar, weight, etc. So the idea here is that we should be able to predict a person's risk factor associated with the heart disease based on some linear combination of these factors here. So what is that linear combination? Well, that is determined by beta 0, beta 1, beta 2 all the way up to beta n. For every point here, every cell value here, there is a column associated with that in the particular A matrix. So beta 1 is associated with the first column, the beta 2 is associated with the second column, beta 3 with the third column, and all the way up to n columns. So the question here is, what combination of beta 0, beta 1, beta 2 all the way up to beta n is going to help us predict the risk associated with the person as close to the original risk as possible? We achieve this by ordinary least square regression, and we can see how it is done visually. Here, just for the sake of simplicity, let us consider beta 1 and beta 2. The loss function associated with beta 1 and beta 2 can be represented by this for this particular training set. Now, when the training set changes, the loss function also changes. So as a result, let us see what happens when we have a different training set. So we have a difference of loss function, and now we have a different set of beta 1 and beta 2. So we initially had a beta 1, beta 2 at this location, and when we change the loss function for a different training set, we got a different beta 1 and beta 2. So the optimal parameters itself change. So that means there is a lot of variance in the estimates of beta 1 and beta 2 for ordinary least squares. So this is a problem when it comes to making some physical interpretations out of that. For example, if I have a high value of beta 1, then I understand that the corresponding column, age, is an important factor. But when I run it on a different set of training data, and now I get beta 4 to be having the highest value, then probably I am messing up my understanding of which parameters are most important and which parameters are least important. Now, in the 1960s, Tikhonov found that there is a solution for this. We can reduce the variance associated with this optimal betas by including an additional term into this objective function. Let us write it down. So this method proposed by Tikhonov is called RIDGE regularization. And the objective function of RIDGE regularization will be like L beta is exactly the same thing plus an additional term, which is the norm of beta. and this is the second norm here. Now let us try to visualize what happens when we add this norm term to the objective function. Basically, we are bringing in a constraint. Here basically we are trying to minimize the error in estimates while also minimizing the coefficients. So it is as if we are saying to the objective function that we need a smaller beta. It doesn't matter if we have a larger loss or not. So in that case, we have this yellow point here, which is the optimal solution. But again, if we try this on a different training data set, we can see that the variance, the beta 1, beta 2 that is estimated, it's almost very close to the beta 1 that is beta 2 estimated from the previous data set. So it basically says that irrespective of the training data, my variance in the beta 0, beta 1 estimates will be minimal. So now in this context, I am selecting coefficients such that I can get most prominent features to get equal relevance. Now in 1996, Tipshirani, another scientist, performs a different regularization technique called lasso, which has some interesting properties. So the objective function of lasso goes like this. It is the same objective function of linear ordinary least square regression plus the norm that we take here is the first norm instead of the second. So what happens in the solution space in that context? Let us see that. In the solution space, we have rhombus-shaped norm isolines instead of circular ones. So what benefit does it have? You can clearly see that the intersection point of the loss function with the norm isolines happens at one of the axes. And what happens when the intersection happen at one of the axes? Here you can see that you only need to worry about beta 2 value. So beta 1 value is irrelevant. This means that in the solution space, we have some coefficients which are 0. That means that there will be some coefficient in this vector which are 0. As a result, this completely ignores some of the features which are least relevant in reconstructing our result. Now let us see what if the loss function changes. Even if the loss function changes, the pointy nature of the isolines associated with the L1 norm allows us to find the sparse solution even in the situations. So using lasso regularization, we'll be able to simplify our model in the sense that we will be looking at only a small subset of the entire set of features which will be used in predicting our risk factor associated with the patient. Now I hope you understand how regularization is used in the context of regression to simplify the models, and I hope this video was useful to you. Thanks for listening and see you in another video.